now let's look at the process flow diagram of the sulfur as well. So we have a lot of processes, but one of the two important things is the reactor and the absorption. So reactor, the function is to convert reactants into desired products by the presence of catalysts. So the process would be the conversion of SO2 into SO3 with the presence of vanadium oxide. And the second part is the absorption, which is the separation of mixture based on gas solubility in liquid solvent. The process would be SO3 gas is dissolved in concentrated H2SO4 in the absorption tower to form olefin. That's all from me. Let's head to the calculation.
For this part, we have two processes that have the mass balance and the energy balance. For the diagram, we have an absorption column with 4 gases and 1 liquid. In the inlet for the gas, we have sulfur trioxide, sulfur dioxide, oxygen, and nitrogen at 500 degrees Celsius 1 atm. And for the liquid, we have sulfuric acid at 25 degrees Celsius 1 atm. However, not all of the sulfur trioxide goes out because 98% of it is absorbed and goes out in the liquid outlet at 100 degrees Celsius 1 atm, and for the rest of the gas at 700 degrees Celsius. In the mass balance for the first calculation, we have the overall balance. After we calculate the number of moles of the inlet in the gas column and the mole fraction for the anodes. After we go to the next process, that is the energy balance calculation. In this part, we only have to calculate the specific enthalpy because all of the flow rates were calculated in the mass balance. However, we could also use a table to get some of them. To finish the process, we calculate the rate of enthalpy for all the components.
Now we proceed to another unit operation, which is reactor. Here we have the combustion of sulfur to form sulfur dioxide in a burner. 100 mole per second of gas is fed to the burner and 1000 mole per second of air is fed to the burner. To find the output and compositions, we must perform mass balance. We know that air contains 79% of nitrogen and 21% of oxygen. So multiply that with 1000 mole air to get the flow rate of oxygen and nitrogen. To get the flow rate of SO2, we must perform the stoichiometric ratio in which 100 mole of sulfur is consumed is equivalent to 100 mole of SO2 produced. It's also equivalent to 100 mole of O2 consumed. The outlet of O2 will be the mole of O2 fed minus the mole of O2 consumed, which is 165.82 mole. The outlet of nitrogen remains constant since there is no reaction. Our next step is to determine the heat reaction. So we must perform energy balancing. In this case, we are using heat of formation. S stream and air stream in which nitrogen is negligible are 25 degrees Celsius and 1 atm. The outlet stream is 500 degrees Celsius, 1 atm. Now we set the reference state to 25 degrees and 1 atm. Since the initial stream is the same as the reference state, the enthalpy would be 0. But since we chose heat of formation, we must add up its heat of fusion value respectively. On the outlet stream, the temperature increases from 25 degrees Celsius to 500 degrees Celsius. To calculate this, we must use the integral of specific heat capacity of SO2 by referring to the appendix. After we get all the enthalpies, we can calculate the heat of reaction like this. N out times H out minus N in times H in, and then we get the final value.
Alright, so now I want to explain about our diagram. This is a specific one. So for part 1, part 2 and part 3. So for part 1, part 2 and part 3, we got commercial steel for the types. For the diameter, we got 4 inch for part 1, 6 inch for part 2 and 4 inch for part 3. So next for the volumetric flow rate, 0.1 for part 1, 0.2 for part 2 and 0.1 for part 1. Next for the fitting, we got 1 gate valve 390 degree standard elbow for part 1, and we got 1 gate valve for part 2, and then we got 1 standard 90 degree elbow for part 3. So for the length, we got 50 for part 1, 30 for part 2, and also 50 for part 3. So for the friction loss and pressure drop, we will show our calculate in other presentation, okay?
For calculation of part 1, we assume Q is 0.1 meter cube per second and we get velocity 12.18 meter per second. By assuming pressure of the burner is 1 atm equal to 101325 Pascal, we can calculate this constant value which is 129.91. So next, we use equation of state which is P equal to rho RT and get the CT equal to 0.6127. For Renault number, RE equal to rho V d over mu, and we get RE equal to 23847.95, which is fuel flow more than 4000. Then we calculate friction factor using that formula and get 0.0065. So after that, we assume length equal to 50 meter because we have 3 90-degree standard elbow and 1 gate valve. K fittings equal to 2.35, KE equal to 1, KC is 0.5. So we can get friction loss using that equation and get 1228.56 joule per kilogram. Using Bernoulli equation, we can assume that lash time V2 equal to 0, no pump and no turbine. So pressure drop, we can get negative 812.84 Pascal. And for pipe 2 and 3, we just repeat the steps that shown in slides. The final pressure drop for pipe 1 and for pipe 2 is negative 1210.28 Pascal, and pipe 3 is negative 1653240 Pascal.
So I will start my explanation for this part. Safely storing sulfuric acid in bar requires careful attention to temperature consideration. Carbon steel tank effective for quantity over 10,000 gallon operate optimally with concentration of 93 watt%. And higher, but temperature must stay below 1000 Fahrenheit to prevent corrosive action. Despite their sustainability, carbon steel and H2SO4 reactive nature mandates regular inspection to combat progressive corrosion. In contrast, high-density polyethylene tanks suitable for volume under 10,000 gallon offer non-reactive with sulfuric acid but require critical temperature. Kept at around 130 Fahrenheit, fiberglass reinforced plastic tank is storage for concentration above 80%, risk corrosion of vinyl ester resin, especially at extreme temperature of 100 to 120 Fahrenheit and beyond potentially. Compromising structure stability. In essence, choosing sulfuric acid storage multi-class attention to temperature detail with specific guidelines for different tank material to ensure safety and integrity.
This is the calculation for a work pump that is located 3 meter from the ground. We assume Q equal to 0.1 meter cube per second. We get the velocity of 12.18 meter per second, and we calculate the Reynolds number and get 1245526.78, which is turbulent. And then the friction factor is 0.0043 because we have two 90-degree standard elbow and the K fitting is 1.48. KE is 1 and KC is 0.5. By assuming length equal to 50 meter, we get the friction loss 843.43 joule per kilogram. We use Bernoulli equation and assume that elevation is 3 meter. Lash time, so V1 and V2 is 0, no pressure drop and no turbine. And we get work pump equal to 871.86. And using the calculation to get the work pump power, our power of the pump is shown in the slides.
Regarding the design process, the tank used is made of steel. Steel is chosen as the material for the storage tank and its components due to its excellent resistance, wide chemical resistance, sturdiness and durability. These properties make steel tanks ideal for storing chemicals. It has a height of 12 meters, a capacity of 60,000 kg and a diameter of 30 meters. We also mentioned the specification of the pipes used, which include a 4-inch schedule 40 pipe and a 6-inch schedule 40 pipe made of commercial steel. The pipes have a length of 30 meters and a diameter of 0.10266 meters and 0.154 meters respectively. Additionally, we mentioned the choice of fittings, which include 2 gate valves and standard 90-degree elbows. These choices were made based on the properties of steel such as resistance, sturdiness, durability, and chemical resistance.